Hey everyone and welcome. Have you ever stopped to think about how a single power source like the battery in your phone manages to send just the right amount of electricity to all the different parts? I mean, how does the current know where to go and how much to send where? Well, that's exactly what we're going to break down today. The really elegant principle of the current divider. So let's frame the problem. Imagine you have one power source, just one single flow of electrical current, but you need to power two different things. And maybe they need totally different amounts of that current. How in the world do you split that flow? Well, the answer is all about a fundamental design called a parallel circuit. See, unlike a series circuit where everything is just in one long line, a parallel circuit gives the current multiple branches or paths that it can travel down at the same time. And it's at that split, that junction, where all the magic really happens. Okay, so the current gets to this fork in the road. How does it decide which way to go? It actually follows a rule you've probably heard before. It takes the path of least resistance. Let's see exactly what that means for our circuit. The easiest way to get your head around this is to think about water. Picture a big river that splits into two smaller streams. Now, if one of those streams is super wide and clear, and the other one is narrow and full of rocks and junk, where's most of the water going to go? It's going to rush down that wide, easy path, right? Well, electricity behaves in the exact same way, so let's translate that back to our circuit. The path with low resistance is our easy route, so it gets way more current. The path with high resistance, that's the hard route, and it gets less current. That's a simple inverse relationship. The lower the resistance, the more current you're going to see flowing through that branch. And that brings us to the official definition. A current divider is really just a fancy name for a parallel circuit that's set up to do exactly this job, to take a total amount of current and neatly divide it up into smaller predictable currents that flow through each of its different branches. Now, we could calculate the split every single time using the basics, like Ohm's law. And we're going to walk through that logic real quick so you can see how it works. But definitely stick around, because right after that, I'm going to show you the shortcut, the really elegant formula that makes this whole thing so much easier. Alright, let's use a real example. Say we've got a total of 10 amps flowing into a split. Path 1 has a 10 ohm resistor, we'll call it R1, and path 2 has a 30 ohm resistor, R2. Now, just based on what we said, we'll already expect more current to go through R1, right? Cause it has the lower resistance. So, doing this the long way takes 3 steps. First, we'd have to find the total combined resistance of those two parallel paths. 4, 10 and 30 ohms, that works out to 7.5 ohms. Second, we use Ohm's law to find the voltage across that whole section. So 10 amp asterisk 7.5 ohms, that gives us 75 volume. And finally, step 3, we use Ohm's law one more time, but just for the branch we care about. 75 vol / 10 ohms is 7.5 amp. It works, but it's a little clunk. But what if we could just skip all that and do it in one beautiful step? Well, we can. That's exactly where the current divider formula comes in. This is the awesome shortcut that engineers use all the time. Here at ICE, its general form. This basically tells us that the current in any given branch, we'll call it X, is just the total current multiplied by a ratio. And that ratio is the total equivalent resistance of the parallel section divided by the resistance of the specific branch you're looking at. It neatly packs all 3 of those previous steps into one clean equation. Okay. Now, for the most common case where you just have 2 resistors, this whole thing simplifies down even further. But here is the key, and it's a little counterintuitive, so listen close. To find the current for R1, the resistoria put on top of the fraction is actually R2, the other resistor. Now, why is that? It's because the split isol about the ratio of the paths. If the other path has a really high resistance, it's going to force a bigger share of the current through the path you're measuring. So, let's just break down the parts of this handy formula. We're resolving for I1, right? That's the current through our first resistor. We take the total current and multiply it by a fraction. And here's the trick again. The top of that fraction is R2, the resistance of the path we aren't solving for. The bottom is just the sum of both resistances. Simple as that. Okay, let's plug in the numbers from our example. You'll see just how fast this is. We start with our total current, which we know is 10. Next up, that crucial fraction. Since we're looking for the current in R1, weighing to put the value of the other resistor R2 on top. So that's 30 ohms. And for the bottom of the fraction, we just add our two resistor values together. So 10 ohms plus 30 ohms gives us a total of 40 ohms. So what we have is 10 amp asterisk the fraction 30 over 40. A little quick math, and that gives us 7.5 amp. Boom. Exactly what we found the long way, but in like a tenth of the time. So, just like we calculated, our 10 ohm path gets the lion's share, 7.5 amp. That means the other 2.5 amps must be going through the 30 ohm path. And look, it all adds up perfectly back to our original 10 amps. The path with 1/3 the resistance got 3 times the current. It works out exactly like it should. Okay, this is a pretty neat trick for solving circuit problems, but why does it actually matter? Like, where does this show up in the real world? The answer is pretty much everywhere. Current dividers are used all the time to deliver very specific amounts of current to different parts of a circuit. They are absolutely critical for setting up transistors to work correctly. That's a process called biasing. You'll find them in all kinds of sensors and measurement tools. Really, they are a fundamental building block of modern electronics. So remember, the real takeaway here isn't just memorizing a formula. It's about getting a feel for a fundamental concept of control. This issue we purposefully and precisely tell electricity where to go and what to do to make all of our technology work. Honestly, learning this is one of the first big steps you take from just analyzing circuits to actually designing them. It really puts the power off control right in your hands. So, the only question left is, now that you know how to command the flow of electricity, what are you going to build with it? Thanks for watching.